Okay, in this example illustrating the shockwave concept, we have a rocket that is directly overhead a person. The distance is 180 meters. The rocket is going at 400 meters per second. Let us assume that the velocity of the sound is 343. The velocity of sound is 343 meters per second. So that means the temperature in the air is roughly around 20 Celsius, right? So let's calculate a bunch of things. Let's first calculate what the angle of the cone will be that is made by the rocket, the cone of the shock wave, right? So we see here sine of theta is equal to velocity of sound over velocity of the source. So velocity of the sound is 343 and velocity of source 400. And then we take the inverse sine of that and we get 59 degrees. So that's quite a big angle, right? 59 degrees, like that. Right? So the next thing that we can ask is, how long will it take for the person on the ground to hear this shock wave, right? And then when he hears it, we call this a sonic boom. It's a crackling of the sound. It's like a thunder, right? How long will it take him to hear it? Well, we'll take the distance of closest approach of the sound wave, right? So the distance of closest approach is this one where it makes a 90-degree angle. This is the closest distance. So the sound wave that will reach him will be the one that was made earlier by the rocket. And the sound wave is like this. Like that. So this sound wave will spread like this, spread. And then when this point reaches them, then they will hear the sonic boom, right? This point of the sound wave. So if this angle is theta, right, is 59, then this is going to be angle 31. It's complementary to it, right? And then if that's 31, this is 59. And then if we know that this distance is 180 from here to here, we can say this distance from the sound wave, from the closest approach, right, of the sound wave to the person, this is D, this is 59. So we essentially have a triangle looking like this. This is 180, this is 90, and this is D, and then this is 59. Right? And then this and this angle are the same. So we can say cosine of 59, and then from this we can calculate the distance of the closest sound wave that will reach them, right? And then when we do that, we get the answer 92.6 meters. Right? Well, now we can calculate how many seconds it will take that sound wave to reach him, because we already know the velocity of the sound, right? So the t is going to be 92.6 meters divided by 343 meters per second, right? When we divide that, we get 0.26, right? So the sound wave will reach him quite fast. The other thing we can calculate is how long the rocket would have traveled during that time interval, right? So the distance of the rocket, and this is the distance of the sound. And we multiply it by 400, right? When we do that, we get 107.996 meters, the distance of the rocket. So it's pretty obvious that the rocket should travel faster because it is going farther, right? So it's got 107.996, and then the sound wave will have traveled 92.6 meters, right? So at the end, the picture will look something like this, degrees, like this. So when this cone finally reaches him, he will hear the shock wave, right? Now let's answer the question, what will happen if the rocket is accelerating, right? So how will that change the answers? Okay, so let's say the rocket begins to accelerate right as the rocket is overhead. So let's say the rocket is not accelerating beforehand. It's going at constant speed of 400 meters per second, and then right when the rocket reaches the person and they're overhead, then the rocket begins to accelerate, and their acceleration is equal to 20 meters per second squared. So how will that change things? Well, what will happen is the sound wave that is closest to him will not change. It still will be the same. So it's going to be like this. This distance that we got, 92.6 meters, will still be the same answer, right, from here to here. Okay. Therefore, if that one doesn't change, the the time that the sound takes to reach him will also not change. So t is going to be 0.26999 seconds. The time for the sound wave to reach him will not change either. So what is changing? The only thing that's changing is that the rocket is traveling farther during that time interval because the rocket is accelerating, right? So the distance of the rocket is going to be the initial t plus half a t squared. So we use a regular equation for the kinematics for an accelerating object, right? So we say the initial velocity is 400.26999 plus half times 20 times 0.26999 squared, 5 meters, whereas the previous answer was 107.996 meters. So it's about 1 meter more. It's not that far more, but you can kind of see it is a larger number. And then what's going to happen to the half angle of the apex of the cone? Sine of theta is going to be 343 over, we have to divide the velocity of the sound divided by the final velocity of the rocket. Well, if the rocket is accelerating, the final velocity of the rocket is not 400 anymore, right? So we have V final is V initial plus AT. Then we put here 400 plus 20. So we take the acceleration of the rocket and then we multiply it by 0.26999 and then we get the final velocity. So the final velocity is going to be 402.6999 meters per second. And then we put here 402.6999. So instead of 400, the velocity is larger and the angle is going to get smaller. So theta is going to be sine inverse of that, and then we get 58.4 degrees. 58.4 degrees, so instead of 59, the angle of the cone is a little bit smaller. So what's going to happen, therefore, as the rocket is traveling this way, the cone is getting smaller, smaller. So if the initial picture looked like this, let's say initially it looked like this. Let's say this is 59 degrees, like this, 59, 59, okay, and by the time the rocket is here, right, and then by the time the cone gets here, the cone is narrower, so I'm just going to exaggerate a little bit so you can see visually what it looks like, right? So what happens is that the distance traveled by the sound wave, this sound wave like this, right? The distance traveled by the sound wave has not changed. It's still the same distance, right? From here to here. And the time for the sound wave to reach him has not changed because the distance has not changed. But during that time interval, the rocket has traveled the farther distance and the cone looks a little narrower, like this, right? And that's pretty much all that changes. So what happens if the rocket is traveling up at a certain angle? Let's consider that case. Right? Now, how long will it take for the sound wave to reach you? So let's assume the rocket started here, and then this angle is 20 degrees, right? So then we have here, this is going to be same thing, 59 degrees, angle of the cone, right? Well, we want to determine now what's the closest distance right here, this distance, right? That's 59, this is 20, this whole angle is going to be what? Because this triangle is a right triangle, right, like this. So this is 90 degrees. So if this is 20 and that's 90, this has to be 70, right? 70. And then you subtract 70 minus 59, you get 11 degrees, right? And if that's 11 degrees, this angle is equal to, subtract 90 minus 11, and you get 79 degrees. Okay, so essentially what ended up happening is, in the earlier example, this angle was the same as this. It was 59. If that one was 59, this one was 59. But because the airplane is heading upward, right, this angle becomes 59 plus 20. So it becomes 79, right? So you can concentrate on this triangle like this. This piece here is 11 degrees. And then this is 90, and then this is the 79 degrees. And then this is distance d, and this is 180 meters, right? So now we have cosine of 79 is equal to d over 180. Well, what's going to happen? The distance is going to be shorter, right? this distance is going to be shorter, and the sound wave should reach you quicker, right? And you will hear the shock wave quicker. So when we calculate that, we quite a bit quicker, right? The previous time was 0.25 seconds, a quarter of a second. This is 66 milliseconds, right? So you will hear the sonic boom very, very quickly, okay? So that's the principle we can say of any of these. Depending on what the angle of the rocket is, if it was 10 degrees, this one would be 69 degrees. 59 plus 10 is 69. If this was 30 degrees, it would be 89, right? And then so on. What if the rocket was heading downward at 20 degrees? Sound wave is going to be farther away from you, right? Quite a bit farther away from you than if it was angled up, right? So we can use the same reasoning to argue that instead of cosine 79, you're going to subtract 20 degrees from 59, right? So it's going to be cosine 39. Cosine 39 is equal to d over 180. So I'm using the same argument, right? I did, it was 59 degrees, I added 20, I got 79. And then now I'm subtracting 20 from 59, I'm getting 39. So then the distance is 180 times cosine 39, and then that one comes out to be equal to 93.258 meters. Okay, so the distance gets larger now, and then if you divide that by the velocity of the sound, 343, you get 0.27988 seconds, right? So now it's going to take longer amount of time for the sound wave to reach you, okay? So you can kind of see here different applications of this. A rocket going straight, rocket going up, rocket going down, and also the case where the rocket is accelerating, okay? Thank you very much.